All right, this is our lecture for section 7.3. The essential standard is I can identify the domain, asymptotes, and intercepts of reciprocal and rational functions, and I can use this information to graph these functions. The next few days material might be challenging, but I highly encourage you to dig deep and make sure you do your best to understand the material because it is extremely important as you continue on mathematically into pre-cal and calculus. You will need to understand these concepts fully to ensure your success in those particular topics. So again, reciprocal functions are functions that are in this form. F of x is equal to c over ax plus b, where a, b, and c are constants. The domain of the reciprocal functions consists of all values such that the denominator does not equal 0. So we cannot divide by 0, so because it is undefined. And so the value in that particular function, ax plus b, cannot equal 0. So this is what the graph of the parent function 1 over x looks like. It is a hyperbola. You will see that the domain, again, is the x values is all real except for x equals 0. We cannot have x equals 0 because I cannot divide by a 0. At x equals 0, we have a vertical asymptote, and that at that location, the function is unbounded. It is approaching positive infinity and negative infinity, so it is unbounded. In addition to that, the range of this particular function is all values except for y equals 0. There is a horizontal asymptote because as x approaches positive infinity or negative infinity, we are approaching 0. The f of x or our y value approaches 0. So we have a horizontal asymptote. Transformations of reciprocal functions are shown here. So we can have transformations of reciprocal functions, and they are similar to what we've learned in the past. Essentially, if we have our h value is a horizontal translation, it will shift the graph left or right. In addition to that, our k will be a vertical translation. It will shift our graph up or down. And our a and b values will define our orientation and our shape. It can be stretched or compressed vertically, or compressed or stretched horizontally, or indicate a reflection about the x or y axis, depending on which, if it is A or B. And however, graphing the reciprocal functions, it is easier to use another approach instead of using transformations. So even though reciprocal functions can be graphed using transformations, easier way to graph these functions is to identify the end behavior, which will be our horizontal asymptote, and to determine what happens at all points that are not in the domain, which will be our vertical asymptotes or holes at those points, and then find our x and y intercepts. Horizontal asymptotes will visually show the end behavior of the graph. They show what happens to the function as x goes to either positive or negative infinity. Reciprocal functions will have a single horizontal asymptote. Vertical asymptotes will visually show where a function becomes unbounded. Functions become unbounded when a numerator that is approaching a non-zero number is being divided by a denominator that is approaching 0. So when the denominator is approaching 0 and we have something other than 0 in the numerator, we will have a vertical asymptote. So let's go ahead and do a couple of examples so that we can identify the domain, the asymptotes, and the range of each of the functions. All right, so the instructions are, again, identify domain, asymptotes, range of each of the functions, and graph each of the functions. So first, we see that we have x minus 3 in the denominator. X minus 3 has to be something other than 0. So we know that x cannot equal 3. So our domain is all reals except for x cannot be 3. Okay, so if we were to graph this function at the value of x equals 3, we will have a vertical asymptote because I can't have a value of x equals 3. In addition to that, as x approaches either positive or negative infinity, we can think of x approaching positive infinity or negative infinity, the denominator becomes an extremely large number, and essentially f of x, our output y, approaches 0. As I divide by a bigger and bigger number, I get smaller and smaller and smaller, and I will approach 0. So our horizontal asymptote is again determined by our in behavior. And we hopefully can see that as we approach infinity or negative infinity, our f of x is approaching 0. So our horizontal asymptote is located at y equals 0. What that means is that the range is all reals except for y equals 0. So y is, or 0 is not in our range. Now that we have identified our asymptotes, both vertically and horizontally, we then need to select some key points and graph the function. So the first thing that we might select is our intercept, our y-intercept, and that would be at when x is equal to 0. And when x is equal to 0, I will get my f of x. It'll be 9 divided by -3, and my output will be -3. So I have a point at 0, -3. And again, as x approaches negative infinity, I am approaching my vertical asymptote of y equals 0. And as x approaches, I don't know why I'm making that dotted, as x approaches +3, my function becomes unbounded at that location. I will then need to select a point that's to the right of that vertical asymptote. And maybe we would select x equals 4. And if I select 4, 4 minus 3 is 1. So 9 divided by 1 is 9. And so I have a point of, maybe we call that 4, 9. And as the function approaches x equals 3, it becomes unbounded. And as it approaches positive infinity, it becomes, it approaches y equals 0. And that's what our graph would look like. Let's try another one. So in this situation, the first thing we want to do is define where our domain restrictions are. And we cannot divide by a 0, so x cannot be equal to 0. So we have all reals except for 0, and that is actually the location of our vertical asymptote. That is where our function becomes unbounded. So I have my graph, I have a vertical asymptote at x equals 0. The next thing I want to do is determine what happens at my end behavior. So as x approaches either positive or negative infinity, I'm going to divide by a very large number, and g of x will become 0. It approaches 0. So we have a horizontal asymptote at y equals 0. And our range will be all reals except y equals 0. Now we need to find a couple points that are convenient to plot. And maybe we would pick a +1. And at that location, my g of x or y value would be 5. So maybe it's something like this. That's 1, 5. Don't forget to label, by the way. So as the value of x approaches 0, my function becomes unbounded. And as it approaches positive infinity, my function approaches my horizontal asymptote of y equals 0. I now need to graph on the left side of that vertical asymptote, and my a convenient point might be -1. And when x is -1, I output, or my g of x is -5. And I would have maybe a point that looks something like this, -1, -5. And again, as I approach x equals 0, my function becomes unbounded. And as I approach negative infinity, I am going to, my output will approach 0. So my graph would look something like that. All right, let's continue on. You notice I have a +6 here. And if I look back on my transformations, that is my shift to the left or right. So since a +6, I'm going to shift to the left, and we'll see what that looks like. So let's look at my domain. This one we have to write out. 3x plus 6 cannot equal 0. 3x cannot equal -6. X cannot equal -2. So my domain is all reals except for x equaling -2. Can't have -2. At -2, when x is -2, my function becomes undefined. And so I have at that location, I have a vertical asymptote. There is my vertical asymptote. So that is at x equals -2. That was where my function will become unbounded. In addition to that, what happens to the function as x goes to positive or negative infinity? I have a very large number in my denominator. That +6 makes no difference. And I will have an output of 0 as my denominator becomes very large. And so that is the location of my horizontal asymptote. And therefore, my range will be all reals except y is equal to 0. All right, now the next thing we want to do is pick some points to graph on this graph. And maybe we'll pick, let's see, 0. Let's pick 0. That'll be our y-intercept. And so at x is equal to 0, y will equal 2. So x is 0, y is 2. Now we have to, 1 point is plenty. Alex is going to make you plot at least 2. As I approach -2, my function becomes unbounded. As I approach positive infinity, my function approaches y equals 0. Another point that you might pick maybe is -3. -3 times 3 is -9, plus 6 is -3. 12 divided by -3 is -4. So I have a point -3 and -4. Oh, maybe something that looks like that. -3, -4. As my function approaches x, as x approaches -2, my function becomes unbounded. And as x approaches negative infinity, I approach, I need that to be a smooth curve, excuse me. There we go. There we go. Okay. As x approaches negative infinity, I approach y equals 0. All right, why don't you try one yourself? Welcome back. Okay, we have to determine our domain. And we cannot have our denominator to be equal to 0. So x cannot equal 2. At x equals 2 is that's where our function becomes unbounded. And that is the location of my vertical asymptote. So we can go ahead and write that, show that. As x approaches positive or negative infinity, the denominator becomes extremely large. And so my output becomes closer and closer to 0. And so my horizontal asymptote is located at y equals 0. The range is all y values except for 0. Make sure you label, please. Now we have to pick some convenient points for x. And we might pick our first one at our y-intercept. So x is equal to 0. And if you plug that in, we have 0 minus 2, and that's -2. And we have 10 divided by -2, and that becomes -5. So we will plot a point, and we'll call that 0, -5. And we will draw a smooth curve to show that the curve, as x approaches 2, our function becomes unbounded. And as x approaches -infinity, the output approaches 0. Another point that we might pick would be maybe 3. So 3 minus 2 is 1, and I would get 3, 10. So maybe 3, 10. And I would become unbounded as I approached -2, and I would approach 0 as I went to positive infinity. And that needs to be a smooth curve. So let me try that again. There we go. Okay. Okay, hopefully it's starting to make sense. I have in letter E, I have the function given. I need to find my domain. My domain is such that 6x plus 3 cannot equal 0. So I find that x cannot equal -1/2. So my domain is x cannot equal -1/2. At that location is where my function becomes unbounded, and therefore I have a vertical asymptote. X equals -1/2. Okay, as x approaches positive or negative infinity, this first part of my function, 2 gets divided by a very, very large number, and that essentially becomes 0, but I still have a -1. So as x approaches infinity or negative infinity, y will approach -1. And so my horizontal asymptote is located at y equals -1. And my range will be all values except for -1. Something like this. Okay. All right, now I got to find some convenient points. We might want to select x equals 0. If we plug in 0, we get 6 times 0 is 0 plus 3 is 3. So I have 2/3 minus 1/3. And so my output becomes 2/3 minus 1/3 becomes -1/3. And so we can plot that. We'll call that 0, -1/3. And we can draw a smooth curve, hopefully, and show that the function approaches 0 as x goes to positive infinity, and the function becomes unbounded at the vertical asymptote of x equals -1/2. In addition to that, I'll pick another point that's to the left of our vertical asymptote. Maybe we would pick something like, we'll pick -1. So -1 times 6, that's a -6 plus 3, that gives me a -3. So I have -2/3 minus 1, and that gives me -5/3. So that might be something like right about here. So that's located at -1 and -5/3. And again, a smooth curve to show, I don't like that curve, that as x approaches -infinity, my function approaches -1. And as it approaches -1/2, my function is unbounded. That's where my domain or my function is undefined. Okay, let's do another one. F of g of x is equal to -4 over x minus 2 plus 3. The first thing I need to do is find my domain. We know that the denominator cannot equal 0. We find that x cannot equal 2. And at x equals 2 is my vertical asymptote. In addition to that, as x approaches infinity, this first part of my function approaches 0, and then I have a +3. So my horizontal asymptote is located at y equals 3, and my range will be all reals except for y equals 3. And then I will pick some points that are convenient. Maybe we pick x equals 3 so that I have 1 in the denominator. So I got -4 divided by 1 plus 3. And so my output becomes -1. In addition, I want maybe my y-intercept where x is 0, and I get -4 divided by -2, which becomes a +2 plus 3, so that's 5. So let's plot those points. So I get x equals 3, and y equals -1. So I'm something like this. So be careful, because as x is approaching 2, I'm unbounded, and as x approaches positive infinity, I am headed towards that horizontal asymptote, which is y equals 3. When x is 0, my output is 5. So I need to be like this, maybe 0,5. So as x is in -infinity, I'm headed towards my vertical or horizontal asymptote of y equals 3. And as I am approaching x equals 2, I'm becoming unbounded. So it looks something like that. All right, we have 2 that you could try yourself. Welcome back. Again, what is my domain? We know that x cannot equal a -3. So there, okay. In addition to that, that is the location of my vertical asymptote. So that's where x is, my location of my vertical asymptote is at x equals, come on, -3. As x approaches either positive or negative infinity, that first part of my equation becomes 0. -5 is my horizontal asymptote. And so my range is everything except that horizontal asymptote. And there is my horizontal asymptote. So let's draw it, y equals -5. Then we need to pick a couple convenient points. We might select my y-intercept where x is equal to 0. And if I plug in 0 for x, I get 6 divided by 3, which is 2, minus 5, which is -3. Let's plot that. And draw a smooth curve to show that as I approached -3, I become unbounded. And as I approach positive infinity, I am approaching my horizontal asymptote of -5. Let's pick another one that's to the left of my vertical asymptote, maybe -4, which would give me 6 over, or -6 minus 5, so that'll give me a -11. So I'd be kind of off this graph, I would assume. We'll call it maybe here, -4, comma, -11. And again, smooth curve to show that as I approach negative infinity, I'm approaching my horizontal asymptote, which is -5, y equals -5. And as I approach my x equals -3, my function becomes unbounded because of the because at that location, the function's undefined because I would be dividing by 0. So next problem, my domain x is equal to everything except for +1/2, because that's where I am undefined. I can't divide by 0. And that is where my horizontal asymptote is located. And as x approaches a positive infinity or negative infinity, this first part of this function becomes 0. And then I will have my function approaching a +3. So my horizontal asymptote is at y equals 3. And my range are all values except for 3. So let's put that in there. And then I need to select some convenient points for x, and maybe I would pick 0, and we would find my output f of x or y to be equal to, it looks like 2.5, and maybe that might look something like this. Let's see, 1 and 2.5, there we go. And I would draw my smooth curve to show my function approaching y equals 3 as x goes to negative infinity, and becoming unbounded as my x value approaches 1/2. And then in addition, let's go to the right of the vertical asymptote. X is maybe equal to 1. And if you plug that in, you might find, or you will find your output to be 3.5. So we can plot that 1, comma, 3.5. And we would show our curve to look something like that. Okay, I hope that lesson makes sense. And we'll look forward to seeing you in our next lesson.